Oil spilled from a ruptured tanker in a circle whose area increases at a constant rate of 6 square miles per hour. How fast is the radius increasing when the area is 9 square miles? We are given a lot of information here. The first thing we need to figure out is what method we will use to work with an exercise like this. And I see something here, square miles per hour. That sounds like a unit per time, which means this will end up being a related rates exercise. The first thing you want to do when working with a related rates exercise is write down what you know. We know that the oil spill is in the shape of a circle. We know that the area is increasing at 6 square miles per hour. And that we're trying to find how fast the radius is increasing when the area is 9 square miles. For us to represent this value here, 6 square miles per hour, that is a rate of the area with respect to time. So we will call this value dA, how the area is changing, over dt, how the time is changing. Now that we have what we know, we're trying to figure out how fast the radius is changing with respect to time. Since we have all of this information, we need to somehow relate area to a radius. Somehow we need to relate all of this together. If you go back and look at the circle, we know that the radius and the area are related by this equation. A equals pi r squared. Now that we have an equation, we just need to take the derivative implicitly with respect to t. The derivative of a, by way of power rule, is 1. And then we multiply the rate at how the area is changing with respect to time. On the other side of the equation, we have pi times the derivative of the radius r squared by power rule is 2r, and then immediately we multiply by the rate of how the radius is changing with respect to time. We almost have all of the information we need in order to figure out what dr dt is. We know already that the area is 9 square miles. We don't have anywhere to substitute that into our derivative. But we can substitute dA dt being 6, and dr dt we do not know yet, so we will leave it as dr dt. So I will rewrite the equation with the 6 substituted in for dA dt. So we have 6 equals pi times 2r, and dr dt is just dr dt. It looks like we need to know what r is before we can solve for dr dt. Since we know the area is 9, we can substitute that value in here for a in our original equation and solve this equation for r to get a value back for r in our derivative. So 9 equals pi r squared. if we divide both sides by pi, then you get 9 over pi equals r squared. The final step is then to take the square root of both sides, which leaves you with the square root of 9 over pi equals r. So now that we know the value of r when the area is 9 square miles, we can take that and substitute it right in for our r value here. One final step to simplifying this r over here is I want to take the square root of the top to be 3 over square root of pi. That'll make our calculations easier when we are trying to figure out what dr dt is over here. So now I will substitute this value in for r. That leaves us with 6 equals pi times 2 times 3 over square root of pi dr dt. When we simplify this right side down, we get pi times 2 times 3 is 6 pi in the numerator, all divided by square root of pi in the denominator. And all of that is still multiplied to dr dt. In order to solve for this, we multiply both sides by the reciprocal. Square root of pi over 6 pi, which will cancel the 6 pi here and the square root of pi here. And we must do the same thing to the left side. So we will multiply this by square root of pi over 6 pi. And we will also have some cancellation on this left side. The 6's will reduce, and that will leave us with square root of pi over pi equals dr dt. This is the answer for how fast the radius is changing with respect to time when the total area of the circle is 9 square miles and the rate at which the area is increasing is 6 square miles per hour. As another note, this fraction is a rationalized version of this answer, 1 over square root of pi. Either of these answers is acceptable.